Welcome back to JVM Internals Crashcasts. I'm your host, Sheila, and today we're diving into the exciting world of serverless Java. We're currently in our Beyond Expert season, exploring advanced topics and future directions of the JVM. In this episode, we'll be looking at how Java fits into the serverless computing paradigm. Victor, our JVM expert, is here to help us unpack this fascinating topic. Before we begin, let's start with a quiz question for our listeners. Victor, would you like to do the honors?
Certainly, Sheila. Here's a brain teaser for our listeners. In a typical serverless Java function, what's the average cold start time compared to a traditional Java application running on a server? Is it A, faster, B, about the same, or C, slower? Think about it and we'll reveal the answer at the end of the episode.
That's an intriguing question, Victor. It really makes you think about the performance implications of serverless architecture. Now, before we dive deeper, could you give us a quick refresher on what serverless computing actually means?
Absolutely, Sheila. Serverless computing is a cloud computing model where the cloud provider dynamically manages the allocation and provisioning of servers. A serverless application runs in stateless compute containers that are event-triggered, ephemeral, and fully managed by the cloud provider. The name serverless is a bit of a misnomer because servers are still involved, but developers don't have to think about them.
That's a great explanation, Victor. So, if I understand correctly, it's like having a car service where you don't own the car, maintain it, or even drive it. You just say where you want to go and the service takes care of everything else. Is that a fair analogy?
That's an excellent analogy, Sheila. Just like how you don't worry about the car's maintenance or parking in that scenario, with serverless, you don't worry about server provisioning, scaling, or maintenance. You focus solely on writing your code.
Now, let's bring Java into the picture. How does Java fit into this serverless paradigm? Are there any specific considerations we need to keep in mind?
Great question. Java has been adapting well to the serverless world, but it does come with some unique considerations. Traditionally, Java applications were known for their longer startup times and higher memory footprint, which can be challenging in a serverless environment where rapid scaling and efficient resource use are crucial. However, the Java community and major cloud providers have been working hard to optimize Java for serverless use cases.
I see. So, what are some of the popular serverless platforms that support Java, and how do they address these challenges?
The major cloud providers all support Java in their serverless offerings. AWS Lambda, Google Cloud Functions, and Azure Functions all have Java runtimes. These platforms have implemented various optimizations to improve cold start times and reduce memory usage. For example, AWS has introduced the Custom Runtime API, which allows for the use of lightweight Java runtimes like GraalVM Native Image or OpenJ9 with Cloud Native Compiler. GraalVM and OpenJ9 are optimized Java environments that offer faster startup times and lower memory usage, which are crucial for serverless applications.
That's fascinating. It sounds like there's been a lot of innovation in this space. Could you tell us more about these optimizations? What exactly is a cold start? And why is it so important in serverless computing?
Certainly, a cold start refers to the time it takes to start up a new instance of a function when one isn't already running. In serverless, functions can be spun up and down rapidly based on demand. A cold start occurs when a function is invoked and there are no existing containers available to serve the request. Java's traditionally longer startup times can lead to noticeable cold start latency. To address this, techniques like ahead-of-time compilation, used in GraalVM Native Image, can be employed to create smaller, faster-starting Java applications. Another approach is keeping a warm pool of pre-initialized Java runtimes ready to execute functions, which some cloud providers implement behind the scenes.
That makes sense. It sounds like there's a trade-off between the flexibility of serverless and the performance we're used to with traditional Java applications. Are there best practices developers should follow when writing serverless Java functions to mitigate these issues?
Absolutely, Sheila. Here are a few key best practices. 1. Keep your deployment package small. Use only the dependencies you need and consider using tools like ProGuard to remove unused code. 2. Minimize the use of class loading and reflection, as these can slow down startup times. 3. Use Java 11 or later, which has better support for cloud-native and containerized environments. 4. Consider using frameworks designed for serverless Java, like Quarkus or Micronaut, which offer fast startup times and low memory footprint. 5. Implement proper error handling and logging, as debugging can be more challenging in a serverless environment. 6. Design your functions to be stateless and idempotent, as you can't rely on local state between invocations.
Those are great tips, Victor. It seems like serverless Java requires a bit of a mindset shift from traditional Java development. Speaking of which, are there any common pitfalls or misconceptions that developers should be aware of?
You're right, Sheila. One common misconception is that serverless means you don't have to worry about scaling at all. While it's true that the platform handles much of the scaling, you still need to design your application to be scalable. For example, avoid using shared mutable state or relying on local file systems. Another pitfall is over-provisioning resources. It's tempting to allocate more memory to your functions to improve performance, but this can lead to higher costs. It's important to profile your functions and find the right balance between performance and cost. Lastly, some developers underestimate the importance of monitoring and observability in serverless environments. Since you don't have direct access to the underlying infrastructure, good logging and monitoring practices become even more critical.
Those are excellent points, Victor. Now, as we're nearing the end of our episode, could you share your thoughts on the future of serverless Java? Where do you see this technology heading?
I believe the future of serverless Java is bright, Sheila. We're seeing continued improvements in Java's performance in serverless environments. Projects like GraalVM and OpenJ9 are pushing the boundaries of what's possible with Java in terms of startup time and memory usage. Additionally, we're seeing more Java frameworks and tools being optimized for serverless use cases. I expect this trend to continue, making it easier for Java developers to build and deploy serverless applications. Furthermore, as serverless platforms mature, we might see more advanced features like improved state management and better support for long-running processes, which could open up new use cases for serverless Java applications.
That's really exciting, Victor. Before we wrap up, let's reveal the answer to our quiz question. What's the typical cold start time for a serverless Java function compared to a traditional Java application?
The answer is C, slower. Typically, a cold start for a serverless Java function is slower than starting a traditional Java application that's already running on a server. However, it's worth noting that once a function is warm, subsequent invocations can be very fast, often faster than traditional deployments.
Thank you, Victor, for that insightful discussion on serverless Java. To summarize the key points for our listeners. 1. Serverless computing allows developers to focus on code without worrying about server management. 2. Java has adapted well to serverless, with major cloud providers offering support and optimizations. 3. Cold starts are a key consideration in serverless Java, with various techniques available to mitigate their impact. 4. Best practices include keeping deployment packages small, using modern Java versions, and designing for statelessness. 5. The future of serverless Java looks promising, with ongoing improvements in performance and developer experience. In our next episode, we'll be exploring the future of the JVM, starting with Project Loom and virtual threads. Don't forget to subscribe to our podcast and leave us a rating if you enjoyed this episode. Until next time, keep diving deep into the JVM.